Today we are going to derive the velocity of light using Maxwell's equations and the electromagnetic wave equation. First, we are going to look at Maxwell's equations. First, we have Gauss's laws for the electric and magnetic fields, where we have defined the divergence of electric fields based in terms of the charge density enclosed within a Gaussian surface, and we have the divergence of the magnetic field, which is always zero, because if you were to enclose a magnetic dipole with a Gaussian surface, the net magnetic flux is always zero. Then we have Faraday's law, which describes the curl of the electric field in terms of a changing magnetic field, or more specifically, it's equal to the negative derivative of the magnetic field with respect to time. And, just like how velocity is the primary derivative of displacement with respect to time. And then we have Ampere's law, which describes the curl of the magnetic field in terms of a changing electric field. More specifically, the primary derivative of the electric field with respect to time. And then this is the electromagnetic wave equations. Basically, the electromagnetic wave equations state that the D'Alembertians of the electric and magnetic fields of light is equal to zero. So basically, the D'Alembertian of a vector, or it's represented, this operator is represented as del sub mu, del sup mu, or represented as a box with a dot. So basically, the D'Alembertian of a vector is defined as the reciprocal of the squared velocity of light as a product of the secondary derivative of said vector field with respect to time minus the vector Laplacian of that said vector field. Secondary derivative as in how acceleration is the secondary derivative of displacement with respect to time. And if you're wondering, the vector Laplacian is defined as the summations of the secondary derivatives of said vector with respect to the x, y, and z axes. So basically, by saying that the D'Alembertians of the electric and magnetic fields of light is zero, basically we can simplify it into these. So the D'Alembertian of the electric field of light is zero, and the D'Alembertian of the magnetic field of light is also equal to zero. Now we're going to do something crazy. So here we have Maxwell's curl equations, we got Faraday's law, and we have Ampere's law. We're going to take the curl of the curl equations. So we're going to take the curl of the electric field and the curl of the, or we can also take the curl of the magnetic field. There are two ways of deriving the velocity of light, so we're going to do both of them at the same time over here. So basically, we are taking the curl of this side, we're going to take the curl of this side also. So we are taking the curl of the negative derivative of the magnetic field with respect to time. So basically, what we are doing is we are taking the negative derivative of the curl of the magnetic field with respect to time, which we can represent as so. You can do the same thing over here. See, by taking the curl of the magnetic field, we are taking the curl of this entire term. So basically, what we have over here is the product of the permittivity and permeability of free space in terms of the primary derivative of the curl of the electric field with respect to time, which we can simplify to this. Now, if we were to remember Maxwell's equations, here according to Ampere's law, we have the curl of the magnetic field in terms of the derivative of electric field with respect to time in accordance to Ampere's law, and we have the curl of the electric field in terms of primary derivative of change of magnetic field with respect to time in accordance to Faraday's law, and we can substitute it. So yeah, so we substitute the curl of the magnetic field with this term to obtain this expression. We substitute the curl of the electric field with this expression to obtain this term. So basically what we have over here is the mu naught epsilon naught in terms of the derivative of the electric field with respect to time with respect to time. So what we are having here is essentially a secondary derivative, and of course, and it has a minus value over here. This expression is negative. So basically, the curl of the electric field is thus the negative secondary derivative of the electric field with respect to time as a product of mu naught epsilon naught. So we can obtain the curl of the electric field is equal to minus mu naught epsilon naught as a product with the secondary derivative of the electric field with respect to time. We can do the same thing over here, as we can see, as we have substituted the curl of the electric field with this expression. What we have essentially over here is the negative value of mu naught epsilon naught multiplied by the derivative of the magnetic field with respect to time with respect to time, another secondary derivative in essence. So yeah, what we have over here is that the curl of the magnetic field is equal to negative mu naught epsilon naught as a product of the secondary derivative of the magnetic field with respect to time. Now, if we want to simplify this further, we have this very neat identity in vector calculus in which the curl of a said vector field is equivalent to the gradient of the divergence of said vector field minus the vector Laplacian of the said vector field. So that basically what it means is the curl of the electric field is equivalent to the divergence of the gradient of the divergence of the electric field minus the vector Laplacian of the electric field, and the curl of the magnetic field is equal to the gradient of the divergence of the magnetic field minus the vector Laplacian of the magnetic field. So here we have the expressions for the curl of the electric and magnetic fields that we have derived from the electromagnetic wave equation, and now we substitute the two equations so that we have this expression in which the gradient of the divergence of the electric field minus the vector Laplacian of the electric field is equivalent to minus mu naught epsilon naught as a product of the secondary derivative of the electric field with respect to time, and this expression in which the gradient of the divergence of the magnetic field minus the vector Laplacian of the magnetic field is equivalent to minus mu naught epsilon naught as a product of the secondary derivative of the magnetic field with respect to time. Now, as we know from Gauss's first law, the divergence of a magnetic field is always equal to zero. There is no net divergence. So thereby the gradient of the divergence is also zero. So we can cancel. Thereby we can cancel the gradient of the divergence of the magnetic field from the expression because it is equal to zero. And if we were to apply Gauss's law for the electric field for a ray of light or a photon, what we realize is that it is also zero because the charge density there is no charge in light. So thereby the charge, if we were to enclose light by a Gaussian surface, there is no net charge, there is no charge density inside it. There is no charge, thereby no charge density, and thereby we have no divergence of the electric field, and thereby the gradient of the divergence of the electric field is also equal to zero. So we can eliminate it from the reaction from the equation because it is equivalent to zero. Now we have two expressions in which the negative minus the negative value of the vector Laplacian of the electric field is equivalent to the negative value of mu naught epsilon naught as a product of the secondary derivative of the electric field with respect to time, and we have this analogous equation for the magnetic field. So it is we would want to cut this minus minus, but what we will do is that we will take the right side of the equation to this side as positive, and then we will get these expressions in which mu naught epsilon naught as a product of the secondary derivative of electric field as a with respect to time minus the vector Laplacian of the electric field is equal to 0, and the exact same analogous equation we will obtain for the magnetic field. Now if you were to remember earlier, we have obtained this expression from the electromagnetic field equation. We have obtained this from Maxwell's equations. We have obtained this from the electromagnetic wave equation. The D'Alembertian of the electric field and magnetic fields are equal to 0. Now what we observe here is that these two equations and these two equations are analogous in every single aspect except these. So thereby we can conclude that the reciprocal of the square of the velocity of light is equal to the product of mu naught epsilon naught, the permeability of free space and the permittivity of free space. We can take the reciprocal and we can take the square root of both sides, so that we can obtain the expression for the velocity of light in terms of the permeability and permittivity of free space, which is that the velocity of light is equal to the square root of the reciprocal of the product of the permeability of free space as the product of the permittivity of free space, or put it simply, C is equal to the square root of 1 over mu naught epsilon naught.